A quick note on polymerization. We can do carboxylic acid derivative type reactions over and over again with difunctional molecules. Like for instance, here's a diamine and a diacid chloride. Here's a diol and a diacid, and so on. If we have those difunctional molecules, molecules can add over and over to each other, one after another. Okay? That's called step growth polymerization. That's when we have multiple independent reactions that are happening on two sides of the molecule. Right? So this diamine and the diacid chloride, remember an amine and an acid chloride, that was how we made amides. Okay? So if one of these reacts, we now have an acid chloride at the end of this larger molecule that the next amine can add to, and then an acid chloride, and so on. So that's why we make a polyamide, and nylon is the most famous polyamide, for instance. Alcohols and diacids, or alcohols and diacid chlorides, or any number of reactions that we've seen before. That's how we made esters. Right? We can do a Fischer esterification like this to get an ester, or if I had an acid chloride, that would work even better, but that's when we make polyesters, right? And we're all familiar with polyester. So take a look. These are three common step growth polymers, right? Here is a diacid and a diamine. That makes polyamide, nylon, for instance. Polyesters can make things like Dacron, Mylar, Terylene. Polycarbonates, where I have a O, C double bond O, and another O on the other side. That's a carbonate functional group. It's just sort of a two-sided ester, like that. Polycarbonates are things like Lexan. It's a very hard, very durable plastic. So just look carefully, a little more carefully at polyesters. Polyesters happen by, they can happen by a transesterification reaction, right? That's where we're reacting an alcohol with an ester to get a new ester, where this is the alcohol is the nucleophile, the OCH3 of this ester is the leaving group. So here's our new ester, but then the other OH of ethylene glycol can react with the ester of the next molecule, and so on. So that's how we make these polymers. That's how polyesters are commonly formed. If I have a diacid or a diacid chloride, I can make nylon. Nylon 6,6 comes from the number of carbons in the two reactants. So if I have a 6-carbon diacid and a 6-carbon diamine, I have nylon 6,6. Polycarbonates have carbonate groups. So, and I can draw that out a little better. O, C double bond O, O, right, with R's on either side. Those are carbonate groups. If we have diphenyl carbonate as well as bisphenol A, right? Bisphenol A, you're going to recognize its abbreviation, BPA. It's two molecules of phenol linked by a quaternary carbon. So two methyls on this carbon in between it. So let's first take a look at the structure that's formed, right? Where if we have one of these OHs as a nucleophile and one of those as the leaving group, okay, we can make an ester on one side, and then if we do it again, another molecule reacting again with the leaving group. So we essentially have bisphenol A molecules linked by just a carbonyl. So there's bisphenol A, then a carbonyl, then another bisphenol A and a carbonyl, and so on. So that's a polycarbonate, like Lexan. This was commonly used in water bottles, baby bottles, and stuff like that, until they found out that bisphenol A, some unreacted starting material, is always present in there, and when that leaches back into the liquid in the bottle, that can contaminate it and has long-term health effects. So that's why if you're looking for drinking bottles anymore, make sure to look for ones that are BPA free. They did that with baby bottles and so on, like that. So polycarbonates are great materials, but as we've seen, not so good materials for things that are in contact with food. So still, bicycle helmets are made out of them. Many of the newer plastic computers, like Apple's MacBooks and stuff like that, the white plastic things, those are made out of polycarbonate.